Fundamentals of Anesthesiology with me, Pat Nelligan. Understanding gases and vapors. Vaporizers, Part 2. Welcome back. In the previous tutorial, we looked at the basics of vaporizers, why we need them, and why saturated vapor pressure matters. I then discussed draw-over vaporizers and why they are no longer in use, and how variable bypass vaporizers work, why they became the de facto standard in the 1960s through to today. I finished with a discussion of problems associated with conventional vaporizers and how they have been resolved. This time, I'm going to explore the modern history of vaporizers, starting with a discussion about the TEC series, and then I'll divert off to discuss the special case of the technologically difficult Desflurane delivery system. Then we will look at cartridge or cassette vaporizers and finish with how vaporizers are filled. Let's start with a discussion about the different types and brands of vaporizers that are available. You will recall from the previous tutorial that there are several problems with plenum vaporizers. The first was flow dependence. The higher the flow, the lower the inspired concentration of agent. There was also a problem with temperature dependence. The lower the temperature of the vapor, the lower the saturated vapor pressure. So temperature correction became a major driving force in vaporizer development. Then there were problems with tipping and overfilling, leading to vapor in the bypass channel. The other problems with plenum vaporizers are back pressure and pressure pumping. This occurs during intermittent positive pressure ventilation, and it can transiently reduce vaporizer output by altering pressure gradients within the vaporizer. The agent that is put into the vaporizer may be incorrect. That is really problematic. That's like putting diesel into a petrol engine. And finally, multiple agents could be given simultaneously on the manifold if they were all turned on. This is a table that demonstrates the relatively modern vaporizer models over time. One of the confusing things is that the companies that developed different models were taken over or merged with other companies. Two companies really dominate products these days: GE, General Electric, and Draeger. For this discussion, I'm going to focus almost exclusively on the Ohio Omeda Datex or GE system that was the TEC series of vaporizers. But it all really started with this particular product. What you're looking at here is an early Cypane Fluotec vaporizer from the late 1950s. This was one of the first commercially successful precision plenum vaporizers and marks the beginning of the lineage that will ultimately lead to today's TEC vapor systems, and of course, the electronically controlled vaporizers that you probably use in the operating room. Before devices like this, delivering volatile agents was far less predictable. Early vaporizers were simple draw over systems that were heavily influenced by temperature, gas flow, and the patient's own pattern of breathing. They were adequate for ether and other early agents, but as anesthesia became more sophisticated, there was a need for much more accurate control of vapor concentration. The introduction of halothane in the 1950s accelerated that need. Halothane was a potent anesthetic, and small errors in concentration could have significant clinical consequences. Anesthesiologists therefore required a vaporizer that could reliably deliver a precise concentration despite changes in fresh gas flow and operating room temperature. The Fluotec represented a major engineering advance. It incorporated the key principles that are still found in conventional vaporizers today: a temperature compensating vaporizing chamber, a variable bypass system to control how much fresh gas entered the chamber, and a calibrated concentration control that allowed reproducible delivery of volatile agent. If you look carefully at this photograph, you'll also notice several features that immediately identify it as an early design. The polished cylindrical body houses the liquid halothane reservoir. The large vertical side glass allows the anesthesiologist to see the liquid level. The red control dial reflects the era before today's international color coding standards. And on the right hand side is a permanently attached filling funnel, reminding us that these vaporizers were simply filled by pouring halothane directly into the reservoir. Although primitive by today's standards, this vaporizer established the basic architecture of the precision plenum vaporizer. In many respects, almost every conventional vaporizer that followed owes its design to the engineering principles first demonstrated by devices like this. The story over the next 60 years is therefore not one of completely reinventing the vaporizer, but one of progressively refining the original concept. Engineers improved temperature compensation, increased output accuracy, reduced maintenance, added safety systems, and eventually introduced electronic controls. But the journey really begins here. Let's take a spin through the TEC vaporizers. Originally developed by Ohio, that company became Omida, Datex Omida, and then GE. This is the TEC 3 vaporizer, introduced originally in 1969, and it became the workhorse vaporizer of the 1970s. You can see that it looks remarkably similar to the original Cypane vaporizer, but it was technologically significantly different. It was the first widely used vaporizer with automatic temperature compensation. It introduced a bimetallic strip to maintain stable output as the liquid cooled. The body was made of copper, and that acted as a heat reservoir to minimize temperature changes. It had agent specific variable bypass plenum design. It also solved the problem of positive pressure ventilation. And essentially, this became the platform on which all further vaporizers were built. The TEC 4 was used in the 1980s and 1990s. The major difference between this and the TEC 3 was improved concentration accuracy over a wider range of fresh gas flows with a larger, more efficient wick assembly for improved vaporization. And of course, temperature compensation and thermal stability was also improved. There was lower resistance to gas flow than earlier designs. By the mid 1990s, there had been a significant change in how anesthesia was delivered, with significant emphasis on low flow circle systems to minimize wastage and environmental impact, and also to improve safety. This model, the TEC 5, was optimized for low flow, requiring greater accuracy of output at different flow rates. The filling system was improved. It became agent specific, so you couldn't put enflurane in the isoflurane vaporizer. The interlocking mechanism stopped simultaneous use of two different vaporizers on the manifold. This vaporizer could be used in pretty much any conventional anesthetic machine today. The Draeger Vapor 2000 is a similar generation to TEC 5. And what I find interesting about this particular device is that it has two zero settings. Both use the bypass channel. It has an off setting where the vaporizer is parked and the interlock is completely disconnected. It also has a zero position where the vaporizer is primed for use and the interlock is active. So if you have a baffle of different vaporizers on the manifold, and for example, you want to use isoflurane rather than sevoflurane, if the sevoflurane is turned to zero, you cannot operate the isoflurane vaporizer. You have to turn the sevoflurane vaporizer off. The current TEC model is the TEC 7. And again, this is pure evolution. There's higher precision, lower resistance, and improved integration with modern workstations. So these are the modern plenum style vaporizers that most of you are familiar with. And again, since the 1990s, new generations are mostly small incremental improvements rather than dramatic updates. But hang on, you might say. You went from 5 to 7. What happened to the TEC 6? The TEC 6 was designed to solve the problem of desflurane. Desflurane was developed as an inessential commercial product. Remember that in the 1990s we had isoflurane a perfectly safe, reasonably low solubility volatile agent that had minimal metabolism, but it was no longer patent protected. Pharmaceutical companies needed a replacement agent, and that was desflurane, but it had a big problem. Desflurane boils at just above room temperature. Small temperature changes cause large changes in vapor pressure. Using conventional designs would be unsafe due to the variability of vaporizer output, so a different type of vaporizer was required, and this was the TEC 6. It is notable that this was the first vaporizer that needed to be plugged in and powered. It needed to heat up, and crucially, given the low potency of the agent, it had a low agent alarm. The TEC 6 is not really a variable bypass vaporizer at all. In fact, it works on an entirely different principle. Liquid desflurane sits in the sump. The liquid is heated to approximately 39 degrees, and at this temperature, desflurane is well above its boiling point, so it would boil vigorously if left at atmospheric pressure. To prevent uncontrolled boiling, the TEC 6 pressurizes the vaporizing chamber to approximately 1500 millimeters of mercury or 200 kilopascals, 2 atmospheres. This raises the boiling point so that desflurane remains as a liquid in equilibrium with its vapor. But why heat and pressurize the agent? Suppose you simply pressurized the chamber and left it at room temperature. On a winter morning, the vaporizer might be at 18 degrees Celsius. After an hour in the operating room, it may be at 27 degrees Celsius. Although the chamber is pressurized, the saturated vapor pressure of desflurane would still vary enormously with temperature because desflurane has such a steep vapor pressure temperature curve. Even a few degrees change would produce a substantial change in vapor pressure and therefore the injected dose. So instead, the TEC 6 heats the chamber to 39 degrees, well above the likely ambient temperature, and then the heater maintains it at essentially a constant temperature so that the saturated vapor pressure is kept constant. 39 degrees and 2 atmospheres, desflurane is still liquid, but at this temperature and pressure, the SVP is stable. Instead of using a variable bypass mechanism, though, the vaporizer injects a precisely metered amount of saturated desflurane vapor into the fresh gas stream under electronic control. So here we have the heating element, the pressurization, and the injector. The fresh gas does not pass through the vaporizing chamber. This is an entirely different technology, and that's why it had its own designated era model, TEC 6. If you have just started working in anesthesia, you may never have actually seen a textile vaporizer. Rather, you may be using modern cartridge based digital vaporizers that literally plug into what looks like a purpose built insert in the anesthesia workstation. Portable cassette vaporizers were a radical technology when introduced in the 1990s, and they are features of GE machines today. In those machines, the vaporizer is known as the Aladdin cassette. The device has a handle, so it's easy to carry, and there are no worries about tipping. They are relatively lightweight. They are plug and play. You click them in, you click them out, and lock them in place by turning a switch. The workstation automatically identifies the agent from its agent-specific vaporizer. The real innovation is not the cassette. It is replacing the mechanical flow splitting mechanism with an electronic control. A conventional TEC vaporizer and the Aladdin cassette generate vapor in essentially the same way. The difference is not how the vapor is produced, but how the fresh gas is divided between the bypass channel and the vaporizing chamber. In a TEC vaporizer, this is done mechanically by the concentration dial that you twist yourself. In the Aladdin, it is done electronically by the anesthetic machine. So an easy way to look at this is that with the TEC vaporizer, the vaporizer itself mechanically controls the splitting ratio. In the Aladdin cassette, the workstation electronically controls that splitting ratio. The cassette provides the agent specific vaporizing chamber. So all it is a chamber containing the wicks and the liquid. Everything else is done by the electronic workstation. Crucially, there is no bypass channel in the vaporizer itself, and that is why the device can be carried around without the problem of tipping. It is merely a reservoir and a vaporizing chamber. So we really have three types of vaporizers. The variable bypass systems that I covered in the previous tutorial, the heated and pressurized Desflurane devices that started with TEC 6, and the cartridge-based digital devices. Of course, in the Aladdin system, the Desflurane is a hybrid. For sevoflurane, the Aladdin is an electronically controlled variable bypass device, but for Desflurane, it is an electronically controlled injection vaporizer, as that Desflurane needs to be heated, pressurized, and then subsequently injected. Most anesthesiologists spend close to zero time thinking about how vaporizers work these days. They just work. But from time to time, you have to fill the vaporizer. Early model vaporizers had a problem. One had to literally pour the liquid out of the bottle into the device. And this was fraught with risk, as I've previously mentioned. It was possible to put the wrong liquid in the wrong vaporizer. This was resolved initially using keyed filling devices. These are color coded and agent specific filling tubes that easily allow one to fill the vaporizer with the correct agent. And while these devices are great, there is a major drawback. You can have a relatively empty vaporizer, you can have a bottle of agent, but you cannot find the dongle to attach the two. And this is a scary situation if you're alone in the middle of the night in the operating room. Modern integrated agent specific connectors are now used. The connector is embedded or connected to the top of the bottle. Now, this started with Desflurane back in the 1990s because you cannot open a Desflurane bottle, it will literally boil off. You can connect and empty it as needed, but they do vary between brands and manufacturers. There is no standardized connector. One of the most horrifying things that can happen during surgery is if the vaporizer empties, the anesthesiologist doesn't recognize this, and the first thing that they notice is the patient moving or becoming severely hypertensive during neuromuscular blockade. The TEC 6 vaporizer was the first device to have a low agent alarm. Nowadays, most devices have these alarms. All of the cassette vaporizers have them. They also have liquid level windows to reassure the anesthesiologist of the current levels so that you can top up your vaporizer before the case. But what happens if in the middle of the case the low agent alarm goes off? This may be a long case and you may have used up a lot of vapor. If you're using a TEC vaporizer, there is no problem. You can refill this during anesthesia, including Desflurane, but you should not do this for Aladdin style vaporizers. One should have a spare cassette available and swap out the cassettes during the procedure. Alternatively, if you only have one cassette, for example, there may be only one Desflurane vaporizer in the operating suite, you can remove that cassette during ultra low flow, refill it, and then replace it. Remember that the vaporizer is outside the circle, so dilution of the vapor within the circle is minimal if you're using low flow. Let's review this tutorial. We started with a discussion of modern vaporizers, and I specifically went through the different generations of TEC devices. We then discussed why Desflurane was different. Desflurane boils more or less at room temperature, hence the vaporizers need to be heated, they need to be pressurized, and the vapor is directly injected into the fresh gas stream. I then went on to discuss cartridge vaporizers, which are reservoirs for liquid and they contain a vaporizing chamber, but there is no bypass channel within the vaporizer itself. I finish with exploring the different problems with filling vaporizers. Next time, we're going to look at gas flow rates and why they matter and discuss end-tidal control. I'll see you then, and I guarantee you'll learn something.